Let me start by thanking our very kind host, Ugo, and my personal host, Dr. Narichi. Of course, you were helped to a large extent by this beautiful city of Padova, and the food and the wine, which is very different from what we know to be Italian in the US. I'm going to ask for your indulgence in the presentation of my slide to the extent that the title slide, in a very unusual way, will come a couple of slides later. And the reason I want to do that is to put in perspective these two talks that we'll be presenting. I think Dr. Jarvis had remarked on it that we have covered a very large domain of dimensions, starting with the subcellular, going to the cellular, component and system. Even the last few talks were at this level. Carlo presented on the cellular level in single fiber measurements. We will talk about component systems, and that was also the central theme of the EMS and muscle stimulation. This is actually a slide from one of the multi-scale modeling grants that we hope to submit. And the strange part of it is that it's not a continuum. Properties don't just blend from one to the other. There are discontinuities and singularities. A lot of that occurs, for example, a lot of the theory that's developed in terms of how forces and to what extent forces produce works very beautifully in ex vivo measurements as well as in small animal models. However, they often fail when you extrapolate to large animals. And why does that happen? Possibly because there are heterogeneities which are not taken care of when you simply say the entire system is homogeneous. And therefore that leads to an onus in our case to start measuring both structure and function in a heterogeneous sense, to take care of finding out how things vary from point to point. To that extent, therefore, it brings us to our title slide. And what we do out here, what this slide shows, are measurements of two different types. What you see out here are static properties such as this and this one. MRI, most radiologists, 99% of their work they will do with what's known as the bread and butter sequence, in which they look at T1, T2 and proton density weightage, and with that they can look and distinguish a cyst from, let's say, a benign phylloides and so on. But one of the strengths of MRI is that with a little bit of engineering, you can get really in-depth studies and qualities of things that make up that entity to an extent not provided by almost any other radiology modality. Out here, for example, this is called Utes. So when you put in, let's say, a block of food into an MRI scanner, you'll see it's a signal void. When you put in a human being, the cortical bone is signal void. Why is that? The signal that comes in the MRI is only from fluidic protons, when protons are whizzing about, proton being part of the water molecule. But anything that's solidified doesn't produce any signal. Out here, this yellow stuff that you see are fibrocartilaginous tissue in which the protons are sort of anchored in a semi-solid state. And therefore, in ordinary imaging, it will not show any signal. But then you can tweak, and we have engineered sequences. It requires a lot of development in which you can then visualize such tissues. Out here are fibers. This is actually the puborectalis and anal sphincter muscle in females. And you can resort to what's known as a diffusion tensor imaging, in which you can actually look at not single fibers, it doesn't have the resolution, but about 30 of those fibers together. And that again gives you very elegant in-depth information that's not provided by any other modality. And one of the aspects, if you remember your high school physics, one of the rules of quantum mechanics is that you can see an entity only to the best resolution, which is limited by the wavelength of the radiation that you use to probe that matter. Therefore, you can look at crystal structure using X-rays whose wavelengths are, the frequencies 10 to the power 16 to 18. MRI uses radio frequencies whose wavelengths are meters long. And there, in spite of which, you can actually look and see structures which are sub-millimeter, right? And how does that happen? I won't go into that, but it comes from this original name of MRI, which was zygomorphography, where yugna is a Sanskrit word which means the convolution of two different entities. Those two entities being radio frequency and magnetic field gradients, which thereby enable you to see at this level of structure. But as far as physiologists are concerned, this provides a whole different perspective on structure of muscles, which we utilize, and then we take the point-wise information provided by this and these dynamic scans. I'll talk about it later, but this shows the inside of a muscle or the leg as the leg is executing plantar flexion motions, and this therefore gives us a good idea. Here you can see the MG, that's the aponeurosis that's been pulled. Here's the inferior part of the soleus. Here's the anterior part. The FHL doesn't move at all. So it gives very exquisite level of information, which we then take and input into a modeling structure. And why do we do that? We want to be able to predict to the best possible extent what the force production is going to be. Therefore, the work that we present out here stems from a whole series of grants. The first one was by NASA, who wanted us to develop a non-invasive technique by virtue of which we can predict what's happening to atrophied muscle, how is the function changing from space point to space point. That was later on taken up by one of the earlier NIH grants, with which we tried to look at certain puzzles of the human anatomy and physiology. Typically, for example, the muscle fibers contract by about 2 millimeters, 3 millimeters, and yet the movement of the calcaneus is of the order of 3 to 4 centimeters. So where is the amplification coming in? It's, as most of you know, the gear mechanism, and how is that affected by different pathologies such as atrophy and so on. So this helped us discriminate and elucidate some of those mechanisms. The third one was how do things change on inaction in a macro sense. Most of you have been talking about this as well, but in a micro sense, we are trying to look at in terms of force production, what is it that's causing the loss of force production. And this last one we owe a lot to Marco out here. We sat down and started talking about this disproportionate loss of force in aging muscle. And we theorized that a lot of that is because of the ECM and how it mitigates. The second talk by my much better half out here will focus a lot on the subtleties of these different scanning mechanisms and hopefully elucidate better how that loss is brought about. So in this attempt, therefore, we have to develop elegant techniques, new techniques to monitor function and also the architecture. So it was that, and therefore this technique of dynamic cine scan has been done a lot in MRI cardiac, and what happens out there as opposed to MRI of the brain is static. You shove it into an MR scanner, you can take a scan without any problem. My background is physics. That wasn't probably enough challenging for me, so the heart is moving, that's what we started with. And there you can take synchronized photographs by synchronizing the photo taking with the R wave. Therefore, you have a natural triggering mechanism, the QR is complex, and triggering your scans to the R wave allows you to take instantaneous photos of the heart as it goes through its pressure, dilation and contraction cycle. Here, the leg doesn't actually have naturally occurring R waves, but we try to force that. What we do out here is to have the patient lie inside the magnet scanner with the leg inside the coil. The leg is encast in half cast, in which the upper half has been taken out and the leg is then bandaged out here. At the sole of the feet is a fabric pair of optical transducers, so that as the subject exerts regular pressure on that, it produces a voltage which is then set. So he also has a biofeedback trigger waveform which he tries to follow in terms of the pressure he or she exerts. And as he does that, the output that comes out is taken out from, this is a shielded room. All MR scanners are kept in a shielded room, and that is amplified and subsequently, importantly, it is differentiated electronically to produce an R wave, so that what you have out here is, so that red curve is the target curve that the subject tries to follow in terms of exerting the pressure. The green curve, the blue curve that you see is the actual pressure that he produces, and that blue curve is differentiated electronically to generate those trigger waves, which tells the scanner, hey, start taking the photo at this point. And as a result of that, MR, one of the downsides of that is it requires a very large number of photo taking, not to average, but to undergo another mathematical operation called Fourier transform, and you require to take that same image with different variations, about 256 or 128 times. That's what these curves indicate. Each of these curves is essentially that green curve out there, and the blue line that you see is the trigger, and this has to be done about 256, 128. With certain tricks we bring it down to about 70, and Usha will show you some in which we actually bring it down to 20, and you'll see the reason why. And for each of the in each of those curves, within this curve we take about 22 phases of the image of the leg as it undergoes that contraction that we talked about. Out here we have a computer controlled method in which we have a foot pedal, and this is kept inside the magnet, and it is hydraulically moved, and the foot is clamped to that foot pedal, so that actually we were able to do image a totally spinal cord injury subject in which the foot was grabbed. So for people who have had stroke and who are unable to move their foot as per weight, we have a lot of veterans out there suffering PTSD. They can exert force, but they cannot often synchronize it with the target wave. So in those cases, our pedal will allow grabbing of that and moving it back and forth. And we can use this for plantar flexion, eccentric contractions, or concentric contractions, or isometric, as you saw in the previous one. And these are the forces that are produced. We have done this over decades, so we know we have a very high degree of consistency. This is flow imaging, again one of those tricks of MRI, and it shows flow within a tube, a phantom tube, a latex tube actually, in which the flow is out in this direction. As you can imagine, if the flow is in this direction, the flow in the through plane is going to be very less, as in this top to bottom direction. This is called a three-dimensionally velocity encoded imaging, in which we have applied, let's say, to blood flow within an aneurysm. That would allow us to indicate where it's likely to rupture and so on. But we use this same technique to look at flow of the musculature within a leg as they exert different kinds of motion, contractions. This is that same flow that you saw in the pipes, except this is the leg, and color coded. This is the medial gastrocs, soleus, and the intensity of the color indicates in that color scale the velocity of the muscle within that region over this entire body. Now, ultrasound also does this with Doppler, but typically their field of view is much less reduced. We were talking with Martino today morning that yes, it would be great to actually have a wider view, but then again you tend to expand increase the scan time. These are again tricks in which we put in like paint brushes, paint the tissue. This is done by inverting protons by 90 degrees, etc. And you can follow the trajectory of different seed points that you put. Typical application, we put these seed points on the aponeurosis and tendon and see how they change position, what the strain is with respect to exertion of force, and from that find out what the compliance is. Here is an example of how the compliance changes with ULNS, unilateral limb suspension. Controlled atrophy is created as opposed to aging muscles, and what we see out here is that the slope changes from the normal to the atrophy, immediately post atrophy, so that the chain link is made more compliant, so that the muscle fibers, even if they contract at the same rate, the force is not transmitted with equal amount of efficiency to the ball of the foot. But after sufficient amount of exercise, they can be reverted back to their old values. So this was in the Achilles tendon, and we did the same with age duration, how it changes with age. And out here we also looked at the fascicle dynamics. Right? So these are fascicles which are made obvious by a certain type of scanning, fat suppressed imaging. Here are diagram, very nice anatomical image in which we can get precise values of the moment of arm, and then we find out along different parts of the NG. So this is distal, middle, proximal, and this is the point that I was trying to say. It is heterogeneous. Instead of just putting one transducer at one point and presuming that's how much the fiber length is going to be across the entire muscle, we are able now to find out at every pixel point what the fiber angle, the fiber length is, what the pination angle is throughout the length of this of aponeurosis. And by virtue of that, we are able, in terms of our modeling, to get much more precise and well-defined subject-specific force predictions. All right, and this is again results of that. This one shows is fascicle length, pination angle in young and in old subjects as a function of the force that's produced. So here, fascicle length, for example, as the force is increased, you know from basic physiology that the muscle is going to contract. That's what these curves show, and these are different points along the length of the leg. And same with the pination angle. As the muscle contracts, it's going to become reducing in angle, and it shows expected decrease in pination angle with age, and similarly larger fiber length in the other case. This is similar to the compliance that we showed in the control atrophy of ULLS. This is with age, and you can again see that compliance decreases, but this is a non-invasive way of finding out what the compliance is. Ultrasound has a tremendous advantage in that it can use much higher values of force that they can exert. Whereas in MR, because we have to make those 70 exertions, we can only operate at about 30% MVC, which is a severe limitations, which, as Usha will show, we have circumvented now by resorting to very sophisticated techniques in which we cut down the number of exertions to about 20. So with that, not only can we go up to about 60 MVC, 70 MVC for young normal people, but also have senior people do it. Senior people even can exert about 20 MVCs at about 60%. So it's made possible in that sense. So in terms of again of a macro picture, this is the aponeurosis 3D rendering of our MR images, and we tried to find the lengthening and the shortening, and we saw that it shortens in the middle rather than being uniformly lengthening across, and this was possible again by this kind of a macro picture that MRI allows. And this is more classic in the sense that we try to find out what the 3D volumes are by taking relatively simple normal experiments, and this was what we were talking about yesterday. You can actually form 3D structures of these, as shown in the next slide, I think. Again, these are various tricks that we resort to by reducing the number of exertions that needs to be made. This is the result that we get, and I want to bring to your attention. This is during the dorsiflexion. Look at this MG muscle. This aponeurosis has been pulled down. This one remains static. But this aponeurosis has been pulled down, but look at the FHL, it remains flat. So this kind of imaging gives you this tremendous insight into what's happening right inside the muscle under different exertion conditions. We can then put it into a modeling in which we can fit the force tension curve to different types of models, find out the coefficients, and predict what the force is going to be. And these curves actually show the very high degree of force prediction. Remember, that was our original objective of this project. This is again age associated, so we are mixing it instead of the title. It says I'll be talking only about PLS, not really. We are mixing just to make better, efficient use of the time. What we want to do is find out the amount of non-contractile connective tissue as shown out here, and segment them out again in reference to our talk yesterday. Adipose tissue as well as the connective tissue, find out how much of contractile tissue is increasing with aging as opposed to non-contractile tissues, and does that explain the massive decrease in force? And we found it doesn't. This last one, specific force 42% lower in older, but decreased to 29 after we accounted for non-contractile tissues of connective tissue and iron. Basic point being that it still does not account for the entire loss of energy. Again, these are the Ute imaging. I'll not go into too much of content, but it actually gives us therefore a handle on these are the specialized techniques. These are not possible in all plants. I'm almost done out here. But here's a picture in which we can see a young person. The green stuff is the connective tissue. You can see a much greater preponderance of that in the AIDS tissue. But and there's statistical significance in terms of how much more you see in that in senior people. However, it still does not account for the entire loss in energy. These are the volumes again that you can very neatly 3D render from the MRI image, and that reduces by about 7 to 14% depending on the subject and their degree of compliance, but the force reduces from pre-suspension to post by nearly 60%. So there's a huge discrepancy between force and the loss of volume. These were, and then the final thought I want to leave you with are this diffusion tensor imaging, which is a very elegant way of not looking at individual fibers but collections thereof, but it still gives us enormous insight. And moreover, what it does is it allows you to look at, have an idea of how long the fiber is. Well, I'll qualify that. In comparison to the cross-sectional areas. Now, the cross-section has two axes, a short axis, and it's, in other words, it's not perfectly circular, but really an ellipsoid. And that difference is kind of important in terms of transmission of force and lateral force. That will be the topic of the next talk. So lambda 1, lambda 2, lambda 3 are the three eigenvectors that are yielded by these diffusion tensor images. Here are, each of these are small vectors. The color of those, if it is blue, shows that the vector is pointing from the top of the head to the feet, that is superior inferior direction. Red points from left to right, green points from the other remaining Cartesian direction. And this is what you see, MG, posterior compartment of soleus, anterior compartment of soleus, FHL. But now see what happens, and it coincides very nicely with the visible human data that's stored in the NIH. Now see what happens if you plantar flex. All those vectors change their direction. In other words, the vector direction of the fibers is changing its direction. We can do this, and here's what you see over the entire length of the soleus. And the point to be noted out here is that unlike ultrasound, this is a picture of the entire muscle. Alright, so you'll get it over the entire length. It's a 3D, so it's not presumed that if you just see in a small window, small portion of the fiber, that's what it's going to be. It actually, as you probably know, there are curvature of the fiber at this end, and the fiber length itself is not homogeneously equal throughout the entire length. All of that can be revealed by this kind of a macro picture. And further, we can actually look at the fraction of anisotropy. That is, if you think of the fiber as an ellipsoid of American football, there's a long axis, and within the cross section, there's a shortest axis and the short axis. And these things change with age, with atrophy, with dystrophy, and so on. And this method, therefore, allows us to monitor each of those. Usha will next talk to you about how to apply this to the actual case of aging muscles. Thank you.